Let's end this section by taking a look here at this last example of example 7. Let's suppose that A is the area of the region that lies under the graph and above the x-axis for this function here. And this is between x is -5 and x is 1. Now, if I was to graph a picture of this function, one thing that I should note is that the largest value I can plug in for x here is the value of 2, right? Because if I plug in anything larger, I'm going to start square rooting negative numbers. And so if I was going to go ahead and try to create a picture of this square root function, I would recognize here that I'm starting at the value of 2 and that this function is moving backwards. So this is my function of f of x. And of course, if I'm trying to find the area between this function and the x-axis from -5 to +1, then we'll say if 1's right here and -5 is right there, then of course I'm looking for specifically this amount of red area. Now, since I have a nice continuous function here, I know by a previous theorem that this should be integrable. That is, I should be able to set up a definite integral and find its value. But let's take a look here. Part A is going to ask to state a definite integral which is equal to this total area of A. Well, that should actually be really easy to do. Remember, A should just be equal to an integral of the function square root of 2 minus x, put the dx at the back, and then I just state where I'm going to find the area from, -5 to 1. So how can I find the area? Well, again, I do the exact same thing that I did in the last video and that you practiced on example number 6. So let's see, let's actually try it out. I would go ahead and start by computing the width. I would need to go ahead and calculate some stuff for right endpoints. And then, of course, I would need to go ahead and calculate my heights for my rectangles. So delta x would be super easy. I would say my interval is 1 minus -5 units long, so that's 6 units. And I'm going to chop that up into n pieces, so 6 over n. I could say that my xi star is very easy to find. I'm going to start at -5, and wherever the next interval marker is going to end up being, I'm going to move over a full width of an interval I times to arrive at the right side for the ith rectangle. So this would be -5 plus 6 over n times I. Height then is also very easy. I'm going to do f of xi star, and I know that my function here is the square root of 2 minus whatever x is. So I would just plug in my little formula for my xi star, and there we go. So I can easily set up what this area is going to look like. I can say here again that my area, which is of course represented by my definite integral, is going to be equal to a limit as n approaches infinity of the summation as I goes from 1 to n of height of my rectangle, so 2 minus -5 plus 6 over n times I, multiplied by width of my rectangle, 6 over n. Okay, so if I can calculate this limit, I'm good to go. Now, if I think back to what we actually did in the previous examples, and what you hopefully went through and actually did here on example 6, is we had to start actually crunching this out, simplifying the inside, and ultimately we used these facts that were up here in this box. But notice something kind of interesting here. These facts allow us to tackle summations of the following form. They allow us to tackle things that are added or subtracted together, that are maybe multiplied by constants or just are constants. And they allow us to tackle things where I have my value of I raised to third powers, second powers, or first powers. But what sorts of interiors then can I possibly deal with? Right? Like, it becomes then really kind of hard to deal with a function like a square root function because I don't have any rules for what to do with square roots. Right? I mean, that's really difficult. Square roots is not something added or subtracted together. I don't just have like my I raised to an individual power. I don't know how to quite simplify this. However, in all the previous cases, notice I just had things that were raised to a power, added or subtracted together, maybe multiplied by a constant. Same thing here, things raised to powers, added or subtracted together, maybe a constant, right? Like, this is all that I was working with. So these rules actually end up being really great if I'm working with simple polynomials, because that's all polynomials are. Things added or subtracted together, maybe raised to some powers with some constants. But I can't do anything right now with something like example number 7. This limit is extremely difficult to calculate. I'll state this here. This is really difficult to calculate. It's incredibly difficult to calculate with the tools that we currently have. So what we're going to need to do in the sections to come is to figure out some more sophisticated tools to try to tackle definite integrals of increasing complexity. What could I possibly do to finally begin to approach answering a question of what is the integral for this function? That is, what is the area under the curve for this function? Right now, this approach seems a bit too complicated because I don't have ways of tackling things like square root functions. Heaven forbid if a trig function appeared in here, or a logarithm or an exponential function. Those would be messy. Right now, we really only have the tools to deal with nice, simple polynomial functions. Of course, as long as my powers don't get too high. So in the sections to come, you'll see that turn our focus away from actually calculating these sorts of giant limits directly to trying to understand some other ways that we might be able to try to determine these limits much more quickly.